So now that we've established osmoregulation as a specific homeostatic mechanism seen in a broad range of organisms from simple to complex, what we're now going to be focusing on is exclusively on animal homeostasis. And we'll entitle the next couple of flowcharts just that, animal homeostasis, and this will be flowchart 1, so we'll put Roman numeral 1. So just things to be aware of whenever you're talking about homeostasis, remember that definition. Steady state. Remember the idea of maintaining balance, regulating the internal environment by exchanging with the external environment. Themes to be aware of anytime you see this word, and the moment you see that, start thinking of those ideas. So now when we talk about animal homeostasis, again, we're talking really more of a complex animal homeostasis, and what I mean by that is the following. Whenever you're looking at homeostasis, it's actually constrained by the certain life or lifestyle that the animal lives. And what I mean by that is the following. We'll subtitle this next part of the flowchart saying the following. Constraints, okay, so constraints of complex life. So you and I, as animals, as complex animals, as humans, lead these very complex lives full of different moments of homeostasis, full of maintaining and regulating and exchanging. All of these things are going to be actually constrained by certain aspects. Those aspects are nicely highlighted in figure 40.2 of the textbook. And by this figure, if you look at this figure, what you'll also notice is the following. Whenever we say constraints, we're really focusing on functional capabilities of an animal are going to be constrained by their complex lifestyle. So it's a little bit confusing at first, but think of functions that most animals are going to have to utilize. Things like strength, things like movement, going from point A to point B, things like diffusion of substances. We can go macro, micro, whatever it may be. These are all events that are going to occur in a complex animal's life. Even heat exchange, maintaining a body temperature that is just right. All of these moments are going to be dependent on structure. These are functions, strength, movement, diffusion, heat exchange, all functions, all physiological capabilities directly dependent on structure, on anatomy, and more specifically on body size and body shape. So we'll write that out. Body size / shape. So we have a dependency on the body size and shape, and that dependency leads to the amount of strength that we have, the type of movement we're capable of, the amount of diffusion we're capable of, the amount of heat exchange. You get the picture. In addition, because of this dependency between body size and function, between anatomy and physiology, what we can also summarize and state is that body size / shape, both of which are directly related to each other, are going to be limited by certain physical laws. So we'll write that out. Limited by physical laws. Now, when we are looking at these physical laws, we're not going to get too deep into any of complex physics, but we basically just mean that the environment that you live in or the function that you need to do really depends on what your body size and shape is, and you're going to have sort of this coevolution occurring between function and structure, as you'll see. A classic example of body size and shape being limited by physical laws, being limited by maybe even physical environment, is swimming. It's a really common function seen in many, many organisms, and swimming, let's say specifically swimming animals in general. Swimming is a movement. Remember I mentioned movement up here? This is a movement that will be dependent on body size and shape. It will be constrained by body size and shape, and it will be limited by physical laws, as we'll see in just a moment. Take for example, the fact that swimming animals must be in, of course, a water environment. The thing is, a water environment, as nice as it is, it's actually a limitation of some sorts for swimming. And that's interesting to think about. How is it a limitation? It's a limitation because a water environment is inherently, it's physically actually denser and more viscous, harder to push through, than air. So these organisms that are swimming have to really sort of push themselves through this really not hard, but dense and viscous substance that is water. Think about it like this. If you, let's say, move your arm in the air right now, it's pretty easy. But try moving your arm underwater. It's much more difficult. This is a limitation. This is a constraint. This is a physical law that's limiting body size and shape. How can we sort of adapt to this law? How can we adapt to this limitation? Well, let's look. Things that are swimming, animals that swim, will have very key characteristic adaptations that help them combat this limitation, combat the water environment and its limitation. What would be that adaptation? Examples would be the fact that their body is going to be relatively smooth. Their body is going to be relatively streamlined. Really nice and easy to push through that water. And also a classic term that we use here is fusiform. Fusiform is this really sort of aerodynamic, not aerodynamic, but water dynamic, I should say, shape that swimming organisms have, all of which contribute to the overall body shape of a swimming animal. What is this concept all about? Adaptations, such as a smooth, streamlined, fusiform body shape, combat, directly relate to, directly help face and overcome this limitation of denser and viscous water versus that air environment. So swimming animals will be successful because of their body shape that has this adaptive capability. And what do we notice? What we notice is these adaptations are going to be seen throughout the aquatic world. Many aquatic organisms, ORGS for short, are going to have this classical fusiform shape. And that fusiform shape is going to be mainly due to convergent evolution, because a lot of these organisms will converge on the function of swimming and therefore have that fusiform shape. It's not that every swimming organism, because sometimes there's a swimming mammal, let's say like a sea lion, and a swimming fish. Two very different organisms, two clearly not commonly related or common ancestry, they both have a fusiform shape. Why? That's due to converging on that swimming function that needs to be done. Therefore, that's due to convergent evolution. What's the function that we're converging on? The function is, of course, we'll write this out very, very quickly. Function is equal to swimming. We converge on swimming, and therefore we converge on our fusiform body shape. So this is a constraint of complex life. You have to do all these things, but you have to make sure your body is capable of doing these things. You have certain adaptations. Swimming is a classic example of that. In addition, when you look at animal homeostasis, besides these constraints of complex life, we also have to understand a really important concept that we've hinted upon, and that's environmental exchange. So again, when you're understanding homeostasis, when you're discussing homeostasis, you have to remember that there's going to be a critical exchange between the internal environment and the external environment, depending on what is needed, depending on the maintenance and regulation that you're trying to accomplish within the organism. This is shown very nicely in figure 40.3. So take a look at figure 40.3 as we go through this environmental exchange. Whenever you talk about exchange, you have to understand that animals are not closed systems. Animals are not equal to. They are not closed systems. And this is something we've actually mentioned before in Bio 1 when we talked about the laws of thermodynamics. Animals are not closed systems, and I want to make sure that's very clear, so I'll put an exclamation mark. That means they're open systems, in other words. Because they're open systems, they must exchange with their environment. It's a key characteristic of an animal, of a living thing, is exchange with environment. And that exchange is going to involve things like nutrients. We do this all the time. What's it called? It's called eating, right? We exchange our nutrients with the environment. We gain nutrients from the environment. We put them in. We exchange gases from the environment. Classic example, we breathe out CO2 and breathe in O2. Plants the exact opposite, and also waste. All of these materials, just a couple of examples, are all going to be intimately exchanged with the environment. How do we accomplish this as animals undergoing homeostasis constantly? This is all going to be done, and we've mentioned this idea before, done via our nice and awesome internal H2O environment. It's a perfect medium to do this exchange because this is where we can have direct access and movement of goods, movement and exchange across an internal cell membrane. Why across the internal cell membrane? Why should we do that? Remember, the functional unit of life is the cell. And if we want to do any sort of exchange at the tissue level, at the organ level, at the system level, it all must begin at this moment right here. And this is coincidingly going to be with that H2O environment that surrounds every cell as well. And speaking of this idea of cells being the unit of life, animal homeostasis will involve a very classic hierarchical organization. So this is a classic organization that you've definitely seen before of, let's say, animal body plan. So animals have a very hierarchical body plan, and that's because of their multicellularity. Take, for example, the fact that the cell is equal to the basic unit of life, right? Everybody knows this. This is the basic structural and functional unit of life. But animals are multicellular. So what happens when you put a bunch of cells together? You are going to have tissues, of course. And then what happens when you put a bunch of tissues together? You all know the story. We get organs. And then what happens when you put a bunch of organs together? You, of course, get systems, and you put all the systems together, you get the organism as a whole, right? But when we're talking about animal homeostasis, we like to function at the cell and tissue level, and specifically for this lecture, we just want to know that tissues are going to be present within animals in 4 basic types, just to be aware of in terms of our body plan. All animals are going to have 4 basic types of tissues. 4 types of tissues, and we'll even say in animals. And these are just tissues, general classes to be aware of. They include epithelial. We don't need to get into the details. Epithelial will basically be our exterior, our skin, things that are lining. This is a lining tissue. Connective tissue that should be implied by the name, very much involved in connections between other tissues and organs. Cardiac tissue, that's related to the heart. And also, of course, muscle tissue. That's a very functional tissue that helps me write that word muscle, that helps me speak the words that I'm speaking right now. It helps you do the listening that you're doing right now, whatever it may be. All of this is a nice, all-encompassing introduction to what animal homeostasis is about. Be sure to look at figure 40.5 to get a really nice, deep, and detailed summary of epithelial, connective, cardiac, and muscle tissue. You don't need to know the details to the extent of the figure, but it's a good way to drive home the point.